This is section 4.3, how derivatives affect the shape of a graph, content objective 2, which is we want to use analytic methods now to find y-coordinates, intervals on which a function is increasing, decreasing, concave up or concave down, and find all the extreme values and inflection points. So the language objective is I would like you to explain what a test writer might do to force you to use the second derivative test. Before we get into this, we're going to connect to our old knowledge, and we're going to recall that old first derivative test from section 4.1. If you don't remember that, go back and read it. It's in section 4.1. And then we're going to examine the second derivative at those interior max and min points to see if we can illustrate this test. If this is a graph of f, we can see that f prime does not change sign here, so we didn't get an extreme value. We can see that f prime changed from positive to negative on the continuous function of f, so we got a max. We can see that f prime changed from negative to positive on the continuous function, so we ended up with a minimum. And again, changing f primes from positive to negative gives us a max, and no change gave us no extreme value. What we want to do now is we want to extend this to the second derivative. And we notice that at a local max, when f prime was equal to 0 and f double prime was negative because the original curve was frowning, we ended up with a max. Similarly here, f prime was 0 and f double prime was a positive number because the original curve was smiling, and we ended up with a min. So this second derivative test, which is what we want to work on next, is this one. It says if f prime equals 0 and f double prime is less than 0, in other words, looking at our picture again, we have a horizontal tangent and a frown, then f will have a local max. Similarly, if f prime is 0 and f double prime is positive, in other words, we have a horizontal tangent and a smile on the original curve, then f will have a local min. The goal of this objective is to put it all together analytically. So I'm going to have you pause this video and read these 9 steps in your notes because I don't think it's as effective when I read them to you. I'd like you to process what these 9 steps are and then realize that it's rare that you will have to do every step when completing problems. Instead, you'll need to pick and choose which ones are appropriate depending on what is asked. So take a minute and read it. With example 1, we are going to do every step. We want to answer every question. We want to find all the parts and pieces, all the intervals. So on this one, unlike the ones that you will actually do in your homework, you're going to have to do every single step. So our first step is to identify the domain. Well, if we look at the original, it's a polynomial, so there are no divisions by 0, no even roots, and no logs. So the domain will be all real numbers. With step 2, we want to find the derivative of the function and determine the x values for which the derivative is 0 or undefined. In other words, we're finding the critical values. So the first derivative of f will be 3x squared minus 12, which we can then factor into 3 times an x squared minus 4, which is a 3 times an x minus a 2 and an x plus a 2. So we want to know when this is 0 or undefined. It's never undefined, and it's 0 when x is positive 2 or negative 2. With step 3, we want to find the second derivative of the function now, because this is going to help us determine our concavity and our points of inflection. So if I take the second derivative, I get 6x. This one is going to equal 0 or undefined. It's never undefined. And it's 0 when x is 0. So then our next step is to create a labeled sign chart for the first derivative, and then the next step is to create a labeled sign chart for the second derivative. So for our first derivative, we're going to label it f prime, and we will put on it our critical points and our domain issues. There are no domain issues, so all we'll have is our critical points that are negative 2 and 2. If I choose a number smaller than negative 2, say negative 3, and I plug it in here, I'll have a negative times a negative, which gives me a positive. If I plug in a 0, this will give me a positive times a negative times a positive, so I'll have a negative output. And if I plug in a number larger than 2, everything's going to be positive. If I repeat that, so that was step 4, if I repeat that same process now for the second derivative, then the only zeros or issues occur for second derivative at 0. Prior to 0, say at -1, if I plug that in here, I get a negative second derivative, and after 0, I get a positive second derivative. So my next step, step 6, is to put these two together to sketch a graph of f. So if we think about what's happening prior to -2, the original function will be increasing and concave down. So I'm going to be on a frown but rising. So that means I'm on the left side of a frown. I get to be on the left side of a frown until -2. And at -2 I start to fall, but I'm still on a frown. So I'm going to start going down like this. At 0 I change from a frown to a smile, but I'm still decreasing or still falling. So that means I'm going to just kind of shift the concavity. So now I'm smiling instead of frowning, and that happens until 2. At 2, I shift so that I'm increasing and smiling. So now I'm on the right side of a smile. So here's our picture of f now. It's a rough sketch. We don't necessarily have all the highs and lows correctly, but we do have the general shape. So we can see here that we have an inflection point at 0, we have a max, we have a min, and we have intervals of increase, decrease, increase, and concave down and concave up. So our next step, step 7, is to compare the extrema's outputs by evaluating the function's y-coordinates, and then find the y-coordinates that correspond to each inflection point, and then summarize everything. So with step 7, we're going to look at the outputs. So that means we'll have f of -2 and f of +2. So if I plug a -2 into this original function, I end up with 11. And if I plug a regular 2 in, I end up with a -21. Step 8, I do the same thing with the output for the inflection point. So I'll get a 0 and a -5. So now step 9 is where we summarize everything. And in step 9, we're only going to summarize in our free responses, or we're going to use what we see to answer questions on the multiple choices. So first we want to talk about increasing and decreasing. We can say that f is going to increase on the intervals from -infinity to -2. And then again from 2 to infinity, and we're going to put the reason, because f prime is greater than 0. We can also say that f decreases, and actually we should say equal to. We can also say that f decreases on the interval from -2 to 2, because f prime is less than or equal to 0. We can also say information about concavity. So we can say f is concave up on the interval from 0 to infinity, because f double prime was positive. And we can say f is concave down from -infinity to 0, because f double prime was negative. We can also talk about our extrema. So we need to talk about the max and the min. So we can say f has a max, a local max, of 11 at x equals -2, because f is continuous and f prime changed from positive to negative. We can also say that f has a local min of -21 at x equals +2, because f is continuous and f prime changed from negative to positive. The last thing we'll want to do is talk about inflection points. So we can say f has an inflection point at 0, negative 5 because, and here's where we list the 3 criteria required. The first criteria is that f prime of 0 exists. The second criteria is that f double prime of 0 equaled 0 or undefined, and in this case it was 0. And the third thing was that f double prime changed sign at x equals 0. With example 2 now, we're going to follow the same steps. We're going to look at first what the domain is. And in this case, there's an odd root, which doesn't cause any problems, so the domain will be all real numbers again. Our second step is to find the derivative of the function so that we can find critical points. So I can write f prime of x equals 2/5 of x to the negative 4/5 plus 0. Now, in order to find out when that equals 0 or undefined, it's easier to work with if I write it as a fraction. So I'll have 2/5, and on the denominator I'll have the 5th root of x to the 4th power. So this is going to equal 0 never, because the top is never going to equal 0, and it will be undefined when that denominator is 0 or when x equals 0. So my only critical value is x equals 0. Step 3 is I want to take the second derivative and find out when that is 0 or undefined. So again, I'm going to do that power rule. I'll get a negative 8 over 25 times x to the negative 9/5. Again, rewrite that as a fraction. I'll get an 8 over a 25 times the 5th root of x to the 9th. When is that 0 and when is that undefined? It's never 0, and it's undefined at the same place that I had an undefined derivative. So what we want to do next is create labeled sign charts for both. So step 4 is a labeled sign chart for f prime. Notice that we just have a 0, which is undefined. And then step 5 is we want the sign chart for f double prime. And again, we're undefined at that 0. Prior to 0 on f prime, that means I'm plugging in a negative number. I'm going to raise it to the 4th power, which makes it positive, and then the whole output will end up being positive. Same thing will happen on the right side of 0. By contrast, on the second derivative, when I plug in a value that is less than 0 and raised to the 9th power, that's a negative number. So this whole thing will be negative on the bottom, and then a negative on the top will give me a positive. And on the right-hand side, I will have a positive denominator with a negative numerator, so I'll end up negative. Step 6 is to now sketch the picture. Well, here I am increasing and smiling. So that means I'm going to rise, and then I'm going to increase and frown. So what we end up seeing is that vertical tangent that we could have anticipated by graphing odd roots of variables. So we have a vertical tangent here, and the rest of the time the curve is increasing. So with step 7, we want to compare the extremas outputs. So because I did not have any sign change in f prime, there are no extrema. So I don't have any to even consider. Step 8, we want to find the y-coordinates that go with inflection points. So some of you might think that 0 would be an inflection point because f double prime is changing sign, but because f prime was not defined, we don't even have a candidate. So again, we will have no inflection points either. With step 9, we now want to summarize everything. We want to talk about when f increases, when f decreases, and when f is concave up and concave down, and then any extrema. So we can write that f increases on the entire real number line because f prime is greater than or equal to 0 for all x's not equal to 0. We can say f never decreases. We can say f is concave up from negative infinity to 0 because f double prime is greater than 0. We can say f is concave down from 0 to infinity because it is there that f double prime is negative. And we can say that f has no extrema and no inflection points. With example 3, we're going to do it all again, only this time we have a piecewise function. So for the domain, we're going to see that both of the branches are polynomial functions, so they're not going to have any problems at all, and we see that 2 is in the domain because we have that little equals. So the domain in this case will be all real numbers. With step 2, we're going to look at the derivative of f. Well, the derivative of f is the derivative of its respective branches. This will be when x is greater than 2, and this will be when x is less than 2. We can't figure out whether this has a equal to underneath it until we examine the joint. So if I examine the joint here and I plug 2 in, we can see that the limit as x approaches 2 from the right of f is going to be 0. But if I look at the limit as x approaches 2 from the left on f, if I plug in 2 here, I end up with a 7. So I have a discontinuity because those two limits were not the same. And because I have a discontinuity, that means I do not get a derivative at 2. So I can't put an equal sign under there. And I can also now conclude that f prime is undefined when x is 2. Because I'm at that jump discontinuity. And here, when will f prime equal 0? I look at when the branches equal 0. This one would equal 0 at x equals 0, but 0 is not larger than 2, so I get no critical values off of this branch. On this branch, I can see that when x is 0, and 0 is indeed less than 2, I'm going to get a critical point. So I have two critical points, one at 0 and one at 2. If I now look at my second derivative, which is step 3 of the process, I'll have a negative 2 and a 2, and again I do not have a second derivative at the joint because I didn't even have a first derivative at the joint. Step 4 is to put the information from my step 2 onto a labeled sign chart for f prime, and then step 5 is to repeat that same process with a sign chart for f double prime. So we can see on f prime that at 0 I have a 0, and at 2 I have a jump discontinuity, which means that my derivative is undefined. Then again on my second derivative at 2 I'm still undefined. Now if I choose values smaller than 0, that means I'm in this branch and I'm plugging a negative number in, so I get a negative output. In between 0 and 2, I'm still in this branch, only now I'm plugging in a positive number. So that would give me a positive on f prime. When I'm larger than 2, I'm in this top branch and I'm plugging in positive numbers. So I have negative outputs on f prime. For f double prime, prior to 2, my output is 2, which is a positive number. And after 2, my output on f double prime is negative. So step 6 is to now put this information together in a picture. And because I have this jump discontinuity, I have to think about where the branches are in relation to each other. We can see to the left of 2 that I'm going to fall and then rise, and I'm going to be smiling the whole time. So I'm going to get a picture that looks something like this. Notice that on the left branch, when x was less than 2, I'm ending with an open circle. After 2, I now am falling and I'm frowning. So I'm on the bottom half of a parabola that opens down. So we got to decide whether we start up here and fall or we start down here and fall. And if we look at these limit statements that I wrote initially, we can see as I'm approaching that 2 from the left, I end up at a y value of 7, whereas if I approach it from the right, I end up at a y value of 0. So that means that my parabola that opens down is actually going to be below the parabola that opened up. So here's a picture of f, and we're now ready to write all of the summary statements. So for step 7, we want to have our outputs at extrema. Well, there's only one place where we were changing sign on f prime where we had a possible extrema. So we'd have f of 0, spit out, say less than 0, I get a 3. And then I guess I could do my other critical value, which was 2, and when I plugged 2 in, I got a 0 out. We can look at possible inflection point, which we would at first glance think is happening at 2, and the y-coordinate that goes with 2, again, is coming from this top branch, which is 0, but it's not an inflection point, and we'll talk about why in just a second. So with step 9, we want to summarize. We want to say, when do I get increasing behavior on f? When do I get decreasing behavior? When do I get concave up? When do I get concave down? So I can say f is increasing on the interval from 0 to 2. Now the brackets on this is going to be a little tricky because we can see that here at 0, if this entire interval I'm going to be increasing, but I cannot include the 2 because at 2 I jumped down. So if I chose an x-coordinate here and then I chose this as the x-coordinate, I don't have a higher y-coordinate at 2 than I did prior to 2. So I'm only going to increase from 0 until 2, but I can't include 2. And the reason I can say this is because f prime is greater than 0. Similarly, I can say that f decreases on the interval from negative infinity to 0, and then again from 2 to positive infinity. And all the interior points are justified because f prime is less than 0. If we think about concavity, that's our second derivative. So we can say f is concave up on the interval from negative infinity until 2 because f double prime was positive. And we can say f is concave down on the interval from 2 to infinity because f double prime is negative. And as far as the extrema and inflection points, we can say f has no max and no inflection point, but we can say that f has a local min of 3 at x equals 0 because f is continuous there and f prime changes from negative to positive.